the end of the session, and we'll have a dedicated question and answer session, and I'll try to address your questions at that point. So these are the areas that I will discuss tonight, the basics of association mining, what it involves, and how we represent the association rules. There are some quantitative evaluation metrics by which you measure the performance of the rules. And we will see one of the popular implementation of association mining, which is called a priori algorithm, even though there are other algorithms. This is pretty much has become the standard in implementing association mining. And we will see example. The focus is not on R. Pretty much most of the things that I'll cover is captured in the practice exercise, so you will find that in there. This is to show you some high-level information from how you can use the rules and how you can select interesting rules, how you can see the data. So the focus of this lecture is not on R. This is on the concept of association mining. And we will have a question answer session where I'll try to address some of your questions. Okay, what is association mining? It is a type of unsupervised learning, which means you don't need any training data, or when I say training data, you don't need any labeled or annotated data from which you fit a model. So this is an unsupervised learning algorithm where you try to identify correlation or association between attributes or variables in your data set, or could be objects like products, and you try to identify the correlation or the association between those quantities. And that is defined by how frequently those things occur. And when we say frequently, it depends from application to application, and we will see how that frequency is determined using a quantitative measure. But how frequently defined is using some quantitative measure. And associated mining, particularly, you read probably mostly applied in the retail industry, where that is where the association mining actually has been popularized. But it can be used in any transactional data set where you have a large number of transactions and a large number of items in any transaction. So you might want to identify products that tend to be purchased together by customers, so that you can come up with targeted advertisement or improve recommendations. Or you could think of, for instance, search queries for a session to be able to optimize the search, or probably identify words or phrases that tend to be searched together to optimize your query. Or you can apply it in complete other domains where engineering domains or safety domains, in the healthcare domain. So it is domain agnostic, you can apply it, but the way you can leverage or you can use the rules might be different depending on the application. For instance, one example that I give you from my own experience, we use association mining for discovering events in flights. So when you have a flight, a typical flight, and that flight has some undesirable outcome, let's say if its approach is unstable, you try to identify events that happen on that flight, and by identifying the correlation in that flight, you might be able to tell, okay, why that undesirable outcome happened. Now, the way you use that in this context is obviously different from the way you try to analyze the patterns in product purchases. Because in product purchases, maybe you're not interested in why certain customers tend to buy, let's say, books together, some books together. You just want to maximize your profit or revenue by either recommending or optimizing the delivery mechanism of that product. But another example that I gave you, for instance, for the flight, the way you use it to discover why that particular behavior manifested itself is the way it manifested it. So the application might be different, the rules of the application might be different, but you can apply it in any context. So how do we present association rules? You know, we say
resume. Okay, recording resume.
So I believe this is where I stop. So yeah, I keep thinking about how bad it is now, the echo. So we were talking about the representation, the knowledge. How do we represent the rules? So assume a transaction. When we say transaction in general, especially basket, this is another name for association mining, is basket market analysis. So if your basket has, let's say, items that include these 6 items, A, B, C, D, E, and F, so the goal is to identify a collection of items that happen to occur together. Again, that frequency, how frequent, is defined by a quantitative measure that we will see in the next few slides. Now, from these items in your transaction database, if you find A, C, D to be frequent item set, there are a number of potential rules that you can generate from. One of them will be the co-occurrence of AD will also lead to C with some level of confidence. So that is the context when we talk about rules. You have items. From items, you identify frequent item sets, and from that item set, you generate a number of rules based on some confidence, which we will cover. In general, in association model and association mining, there is no single model. Like I said before, there is no a single model that you fit like a mathematical or statistical model. You generate a collection of rules. That rules together make your model. If you use some packages, some statistics packages like HBase's modeler, it is called model. So the way it works is model, but in association mining, it is a data mining, quintessential data mining algorithm where you don't fit any specific model, but a number of rules that make your model. So the knowledge representation is you have item set, in this case, X is a set, leading to another item set in Y. So that's your rule. Items, when you see items in X with the in a set X, that will lead to the observation of another set in Y with some level of confidence. And the left one, formally the left side of the rule is called the antecedent, which is the if part. If X, then Y. And the right-hand side is called consequent, or the then part. An example would be if a customer buys milk, they're likely to buy bread with certain confidence. If another customer buys a diaper, with some likelihood, that customer will also buy beer. So that's how we formulate, how the rules are captured with if and then clauses. So how do we define, remember we talked about how frequent it is. So that frequency depends from application, how frequent it is. It is different from one application to another. Because if you have a large database with sparse data, maybe you have to put the support level lower. So what is support? So the support is a metric, an evaluation metric by which you define or you set a threshold above which you consider the item set to be frequent. So it is in proportion to the total number of transactions. So if you're looking at the given item set, you counted how many times in your transaction, and you normalize it by the number of cases you have in the entire database. So basically, you divide the transaction containing that particular item set by the total transaction. That is just your support. That is the probability of that particular item set given this particular data set. So that is support. Typically, it is set to a low value, primarily because, in general, in the context of discussing transaction database, most likely, especially in the retail application, you have a large number of transactions as well as a large number of items. And that leads to a sparse in data. So unless you put the support value smaller, you won't be able to capture some of the interesting rules. Also, if you think about it, things that happen quite frequently, it's likely we will have enough information about those rules. They will not be interesting. So things that are not obvious that happen infrequently are likely to be interesting. So the support in general, it depends on application. There's no single number, but in general, smaller number. You use a smaller number for the support. So that support helps you to define the frequency of the item set. The next phase is the confidence, how confident you are in a particular rule. So you go through all the items that have been discovered using the support value, and you generate the rules only from those frequent items. So it is a conditional probability. Confidence is a conditional probability of the rule. It is specific to the rule. That means the confidence of a given rule is the probability of seeing the consequence giving the antecedent. So this is a conditional property. Usually you calculate in terms of support, the support of the rule to the support of the antecedent, or the if part of the rule. In this value, usually you tend to put a higher value because you already identified the frequency of that thing, and using the support that you want to have a higher level of confidence for the rule you're generating from the item set. So in general, 80%, 70%, 90%, depending on the game application, but you tend to put a higher number on confidence. Now, by the way, these are not only the only metric. There are a number of other metrics people use, but these tend to be the popular ones associated with the priority algorithm or accession mining. LIFT is another one is commonly used. It combines the support and the frequency, the confidence. Using LIFT, you also try to measure how likely, let's say you identify a particular rule, how likely is that rule could have happened by just pure chance. So LIFT helps you, gives you information about that value. In general, you want to be far from 1. The closer the LIFT to 1, the higher the probability that the particular rule has, occurred just by pure chance. So LIFT provides you that information to be able to compare the frequency of the observed pattern with the expected occurrence of that thing by just pure chance. Another one that goes with LIFT is leverage. Once in a while, people use leverage, which is sometimes a given rule happens quite often. The support is high. The frequency of the item set is high, but there is a corresponding lower LIFT for it. So you might want to investigate that. So using leverage, that balance is counterbalance, because if you just use LIFT, you tend to ignore that because the LIFT is low. But if it happens quite often, you might want to see the leverage to define. It might be still interesting. Okay, so the basics. These are how we represent them, what are the quantitative values by which we measure the performance or evaluate the rules. The next thing is how do we mine? Because at the end of the day, like I said, when you deal with a transaction database, you're dealing with a large number of items and a large number of transactions. So finding the item set is large. The search is very large. So typically in a private algorithm, accession mining implementation, there are 2 phases. The first phase, and for the most part, these phases are independent. The first phase is you discover the items, the items that you, as you defined it, frequently enough. And from those, then the second phase, you generate the rules from this frequent item set. And we will cover in the next slide about those 2. Elena, I don't know how bad or better it is, but let me know if there's anything Okay.
We can't do much about this. It's your phone. So continue.
Okay. So the search heuristic, the mining strategy, in the first phase, like I said, let's say if you have k items, the search space is exponential. You would have 2 to the k minus 1 items. That's a large space. You can't. I mean, when you deal with thousands and thousands of items, very computationally expensive. It's not feasible to apply a brute force to find all the items. So, but there is a nice property that is used by the Prior algorithm. I think it was first discovered by Prior. That property is if a given item set is infrequent. So you set your support value. Based on that support value, if you find an item to be infrequent, any superset of that item is infrequent. So there is no reason to go and search. You can literally avoid all the things that are supersets of that subset. So an example here is you have in your transaction, A, B, C, D is the item. And if you find A, B to be infrequent, then there is no reason for you to continue searching the space that contains also A, B. So A, B, C, A, B, D, every superset of A, B will be infrequent. And this property is called anti-monotone property, and it is used to cut down on the exponential search space. I think I have used the figure provided in the textbook in one of the sources provided in the slide. So in this particular case, the transaction, you have A, B, C, D, right? So you start from the top right here, and then you discover A happens to be frequent, B happens to be frequent as shown here. And then you go to the next combination, which is the two set, so the two item set. And AB happens, if you find AB to be infrequent based on the support value, then you can avoid the search. You can exclude or prune everything below this line, which is superset of AB. So by doing that, applying that property, you can cut down on the search, on the exponential search, quite a bit. And that is, I think, originally discovered by the Prior algorithm. And there are other optimization techniques in addition to this, but this is the primary one in a Prior, because the search space. So that first phase is identifying the items. Once you discover the items, then you have to generate the routes. And the route, when you discover or when you generate the routes, you don't have to actually scan the database any longer, because at that point you have already discovered the items. You just go through the items that are frequent and generate the routes. And each frequent k item, for instance, if you have k item set, it can produce to the k minus 2 association. And the way you do this is you split the item set and try all combination of that thing, the 2k to minus 2. For instance, an example, make it easier. So if I have an ABC, that is the frequent item set that I discovered during the first phase, then the 2k to minus 2 would be 6. There are 6 candidate rules. Those are here, right here listed. A leading to BC, B to leading AC, C leading to AB, and all these are all the potential rules. They're potential because then you apply the threshold set by the confidence whether this is the rule that has satisfied your condition. But these are all the potential rules. Now, the confidence is calculated. The confidence of any given rule is calculated by this formula. You calculate the support of the item set itself over the support of the antecedent part. So that is your confidence. Now, initially, all the high confidence rules the way in a prior algorithm, you start with containing one item. All the high confidence that have you do with the one item, and then you go to the next one while extracting the rules. Now, one thing that's different, if you remember the anti-monotone property that was the case in support, doesn't quite apply to the general case for confidence. That applies only for rules that generated from the item set. What I mean is, let's say if you have this particular rule where items in X leading to an item, you remember once you discover the items, you divide it into two to generate the if and the then part. So that means X leading to the difference between Y and X. If that doesn't satisfy the confidence threshold, so this is the anti-monotone property of confidence, then this rule X prime leading to Y, the difference of Y and X prime also does not satisfy, which means given that where X prime is subset of the X component, it's easier to explain in an example. Let's say you have ACD leading to B. This is your rule. So any subset of this, if this doesn't satisfy the confidence threshold you set, then any subset of the antecedent will not satisfy either. Then every combination of every subset of this, AC leading to BD, AD to BC, CD to D, all of these will not satisfy. So this is another optimization on top of the support optimization that we talked about in cutting the search space. So in graph, I think you can see this in the textbook as well. I took it from textbook. So let's say you discovered this to be, if this does not satisfy, if BCD, I lost my mouse. Okay, if BCD leading to A does not satisfy your confidence threshold value, any subset of BCD won't satisfy either. So CD, BD, BC, D, C, B. So you can prune all this search space. And again, this is when we do the rule generation, we're not passing through a transaction data set. We're just iterating through the item set. But this is additional search improvement using the anti-monotone property. Okay. So these are the basics. So what we looked at is, I hope I have time. Yes, well, 8:29 right now. So what we looked at is how we represent the knowledge representation, the basics, what are the quantitative or the statistic by which we measure the performance of the rule, namely the support and the confidence and the lift, and we looked at also leverage in the two phases of the association mining strategy. So I want to just show you an example using a data set, a book data set, exactly what we covered in the previous slides. So the first thing, typically when you work on a data set, you try to formulate the problem, right? What is it that you try to understand in the data? First, in this context, in the book's context, we want to understand, okay, what is the purchasing pattern, the rating pattern of the customers? Let's say if you have customers, let's say you have a website where people can buy books or rate your books. So you want to understand the pattern. And one scenario is you might consider your customers as transactions, basically. So every rating done by your customer, you can see that a customer. So potential application for this would be you can probably do some recommendation for that customer or learn that patterns and do recommendation for other similar customers, or maybe do some kind of targeted advertising. So the transaction in this case is a customer, and the items here are all the books they have purchased or rated. So in R, the package that's relevant for a prior is called a rules package, and there are a number of functions embedded in that package. Also, there is a corresponding visualization part of the package. It's a separate package, but works on once you generate rules, you want to visualize it, displayed that in a way that can show you the different metrics, the different quantitative value related to the rules. So this data set, you can get it from GitHub, Brooks Data CSV. So a snapshot of some cases here. There is a user ID, your customer ID, the rating provided by customer for a given item or a given book, and the title is that. So in general, and then I think this has been covered in the exercise file. When you work with the data set, when you have a mix of categorical and numerical values or continuous variables, there you have to do some preparation steps. For instance, one of the things that you need to do in numerical values is you have to display that, because a priori cannot directly handle continuous variables, so you have to do some categorization or discretization. Also, you might want to remove unique fields, because the unique field is for all records. There's no reason why you keep that as part of the session mining. But in this particular data set, we're dealing with binary, whether the customer purchased or rated a book or not, the binary. So there's no continuous variable to treat. From my experience in general, association mining is one of the data mining techniques with data preparation that doesn't require as much data preparation as other methods, say regression. With some cleaning, it still have to do cleaning, but it's not quite as other approaches. So what we have here is usually the first thing after you loaded your packages into memory is you read it as a transaction. Now, in this case, I'm reading the book basket. I call basket. I'm giving it the file name, in this case, a tab-separated file. The format is single or basket. If it is single, every transaction will contain an item, one item. If it is basket, every row will have one transaction with multiple items on it. But practically, it's just a format. And I am interested only reading the user ID in the title. I'm removing duplicates for this particular case because it might be possible some customers might have rated the same book just with version difference. So I don't want to trade those instances of different cases. So I'm duplicating those transactions. So once you read your transaction, and when you look at it, for this particular case, we have 9,501 transactions. Those are rows because I use a single format. And there are 220,447 items. It's not a huge, but it's large enough. So this is the first 5 columns of the titles and the row names, which corresponds to the user ID in this case. So transactions and items. So we loaded our data into a transaction format. So we have the transaction in memory. So in general, you want to do some exploration before you just generate rules, because there might be cases that from looking at the frequency and the items, you can still optimize the search space by having a good understanding about the relative frequency of the items. So here what I'm doing is I'm determining what are the typical size. So the book size of the book basket. And I'm summarizing that. It looks like, for the most part, most customers have only one. The median is one. But look here. It looks like at least one person has purchased or rated more than 10,000 books. So I want to investigate that more. If there is an outlier or bad data or something. Or maybe there is something that I can leverage from the way the data is distributed for fitting the algorithm. So item frequency is another function. Size is also another function of the errors package and item frequency. So this is how frequently they happen. And I know I'm normalizing by the the entire transaction by the interaction basket size to get the book count. And I'm sorting that using a sort function here, the decreasing order. And now I'm displaying the first data just to see, what is the frequency of the most frequent item or book. As it turns out here, wild animal is happened 2,500 times. That is the highest in the transaction. And remember, we have more than 200 something items. So that is, if I look at this, if I divide by the basket, the book basket that I defined here, the first one, that is still less than 3%, 0.02% of the transaction. So that tells you the level of sparsity in the data. So even the most frequent item happen less than 3% of transactions. So if you go to, now, again, I'm trying to leverage the distribution for optimizing the frequency. So this is the thing that we saw earlier. I am basically the same information we saw here. I'm just plotting it to see. So as you can see, most of the things happen in the smaller range. See, a larger number of cases or one. This is a frequency. This is a density plot. So now there has to be something I had from this data set. Remember, the reason why we're looking at this data is to be in the problem formulation. We say we want to identify customers that purchase multiple items and rate multiple items. So right out of the box, you can say, okay, for those customers who happen to buy only one book, there is no reason to try to discover rules because it's unlikely, it's impossible to learn anything about pattern matching or any association because they only purchased one or they only rated one book. So I can avoid, so by using the quantile function, I can see the percentile. So all the way to the 15th percentile, customers, more than 50% of the customers only purchase one. So I can eliminate on the entire data that corresponds to only one purchase. And that's what I did here. So I'm keeping only records. I call it the usable one. Again, now the type of cleaning you would do depends on what is your application. But for this particular application, I can simply ignore this interest. So I'm keeping only customers. Again, the customers are my transaction here that purchase books more than one. That reduces the transaction by more than 50%. It was 90-something transaction cases. Now I have only 40,000. So that will help in expediting the search space. So because one of the things a priori does is it does multiple scan of the transaction as it is discovering the item set. So the data cleaning in this particular case is avoiding the cases where it doesn't make any sense to try to generate rules for. So remove more than 50% of the cases. Now I fit my rules using the prior function. Now I'm not going to get into the details of the prior function. You can do a lot more options. You can provide a lot more options. But in this case, I'm providing the support and the confidence. Support is only 0.002 and confidence 70.75, 75% confidence, basically. And then once the algorithm returns this, which has, so it generated this many rules, and the rules, the most popular rules seem to be rules with 3 items. Both the left side, remember, the way we generate rules is from the item set. So the item set contains both the left and the right hand, so you have to add both. So 3 seems to be the popular one in this case. And, we have 11 rules with length 2, and 66 with length 4, and 14 rules with length 5. Now, there is also option to control this, but I believe the default in our prior flag is 10. So it is, in this case, the rules were not able to discover anything in any rule about 5 items. And Now, the information down here is aggregate information is useful, but is not on individual rules level. So aggregate for the rules. But it provides support value, the mean, the median, and basic summary, and the confidence and the lift. And the bottom information here is, how you call that function, the prior function. Now, the next step, again, you can do a lot more with option here. I'm just showing you the basic function. The next thing is you might want to look at the rules that was generated. Yeah, I have 4 or 5 minutes, and then we'll go to the question and answer session. And so here I'm doing the first 5. I'm sorting by confidence, and I'm using the inspect function. I'm looking at the first 5 rules by confidence, and this happens to be the rules in this particular case. If you notice this, for those of you familiar with these books, 4 to score, high fives, 7 snap, and 2 for the door. These are books that come in series, and it is logical to think when you buy a book in series, it just makes sense for you to buy or read the next sequel to that. And this is a Harry Potter series as well, so people purchase this series tend to buy these with a support level of this. That means this person, 43% of the cases of the total transaction, and this is the confidence level, the condition and probability given that items that support in the list. Again, we want the list to be much larger than 1, because if it is 1, it is likely that rule could have happened by chance. Okay. All right. For example, part of the code, you can do another option. You can give it appearance. The appearance helps you control what items to appear in the left side or in the right-hand side. And remember, we only covered the support, confidence, lift, and leverage, but there are a lot more. You can find those. You can evaluate the rules using the function called interest measures function, and then you can list all of them. And those things are covered in the exercise. You can follow the exercise to look at the other matrix. A redundant rule is it's part of because this is natural classification mining, because you are going through a large space, you tend to discover sometimes rules that are redundant. Redundant rules are rules that do not generalize well. So basically, an example is if X leads to Z and Y leads to Z, if both have the confidence level, support level high enough, and also if you have a rule that combines X and Y leading it again to Z with the same level of confidence, the more general would be the X leading Y and the X leading Z and the Y leading to Z independently. So that is the second one will be a more specific case of that. And I think the textbook covers really well what redundant rules is. So you might want to remove that those redundant rules using a matrix. Again, that information is in the how you do it is in the exercise book. Visualization, I won't be able to. We don't have time really to go over visualization. The most part is straight. It's implementation of the flat function using the Aeros Viz package. Where you can generate scatter plot, graph, file coordinate, group data, mosaic graphs, and matrix in 3D. And all those is some way of visualizing the different matrix into rule. And it's really important for you to have a good understanding of the rules generated. So I really recommend you to just spend time, because that's part of the requirement in the exercise and assignment for you to do some visualization of the rules. But I won't be able to cover it here mainly because of time. And there are alternative algorithms. For the most part, my experience with the priori, I have worked a little bit on equivalence class transformation from my own understanding, but there are others that also improve in the search space, as well as some of the things that a priori cannot handle. And
Also, there is a dynamic programming version of the prior algorithm, but there are others as well. I'm sure that you might want to read on. And that will do it. And I'm sorry about the voice quality, but we got to a point where I'll try to answer some question you might have. But I have to figure out how to go to the.
Okay, question can be either posted in the chat or you unmute yourself or raise your hand and I will unmute yourself and you speak. Either way is going to be okay. So I'm looking in the chat and I don't see question yet. Is someone... Okay, I see a question here. Can you hear, Firdo? Can association handle missing data?
Okay. Can association avoid missing data? Yes, but you're not getting any information from missing data. Right, remember, this is association attributes. Let's say you're having X, Y, try to identify if there's pattern in it. Unless you do some kind of estimation of the missing values, then effectively you don't have any data to correspond X with Y. So it is not a unique problem to association mining, but there is no information. So unless you do a preparation, so by providing some kind of estimation, maybe if it's a continuous variable, say by providing an average value, or if it is a categorical value, maybe if it makes sense, regardless of whether you use association mining, providing a typical value for that categorical variable, there's nothing you can learn from association mining. So it cannot directly handle missing data. Unless, in other cases, you can consider the missing value as a separate category if it is a categorical variable, and then you can discover rules for that new category. You call missing, maybe not applicable or missing, you just give it a category and you can discover that. But as far as using that rules, it will be limited because you don't have any information. So in general, this kind of thing is better handled before you get to the association, the modeling part. We will learn another technique, a decision tree algorithm that handles missing cases much better than other algorithms. But missing data is a very challenging problem in data mining. In some cases, there are reasonable estimation techniques that you can do. In some cases, if you have a large data set, you can safely ignore the missing values. But there is no one standard way of doing it. It depends from application to application. Like I said, one technique people do is just give it another category, and you treat that category as a separate value. And now what you do with that information will still be limited because you haven't gathered information for that. So usually estimating will be better, but if it is dual, you can do that estimation.
Fabio, can you see the chat? Because people are not directing the question to everyone. So I see here a question if we are going to have a demo on how to use association in R. I don't think for today we have planned this, but if someone has planned it, let me know.
Okay, there is another question. You can't eliminate the echo by talking.
Our demo, we are going to, we didn't plan for today because today is lecture session. Our is application, we can do this in additional session.
Oh, okay. Okay, that's good to know.
Well, unless you have something and you want to show, but I don't see more questions. Even in my view, I don't see many other questions.
Yeah, I'm looking at the chat session as well. So somebody like, I would love that. Thank you. That would be a response to one of the comments, I guess.
Yeah.
Again, most of the things that I haven't covered much of the art part of the, I try to focus about the intuition of association mining. But in the exercise, there are some steps how you do data cleaning, preparation, and how you do visualization, and how you provide the different options for the a priori function. So in the exercise, and there are other sources in the textbook as well. Okay, thanks for the link. A priori simple. Is that a question, Danny? Priori simple. Can you expand the question?
Is this a statement or a question? I don't.
Oh, got it. So the link you provided was a simple explanation of the algorithm. Okay, thanks. Yeah, I mean, there are a lot of resources. This is one of the algorithms that's very popular in data mining. I think partly because it doesn't assume any theory. You don't have to assume any distribution. You just try to discover patterns, basically. And this is, like I said, the quintessential data mining application where you don't make any assumption. You try to identify patterns. What that's data. That is the pure definition of data mining. For instance, in some of the classical application where we will learn about regression, you do come with some assumptions. And if those assumptions do not hold, the model could be questionable, the validity. And it still might be okay, but you come with this assumption, you want to validate those assumptions are accurate still. Here, that's it, you're discovering patterns. And there has been a lot of research on this, how to optimize the search. A priori happens to be the first one that optimized the search space, and it was commercialized using HSpaces. I think Clemente is the first commercial tool, so it has become popular, and for the most part, that's what people use. And it's simple to use, association mining. I mean, very little data preparation. You can't, yet the search space is large, but if you use some of the packages, R does not quite handle multiple cores, doesn't leverage that. So when you have a large number of items, I mean, at least this is based on my experience, I use HSpaces and other packages to optimize the computing environment because R has some limitation in that regard. But even when you have a large number of cases, you can still discover rules, interesting rules. So it looks like everybody is okay with the material that was presented. And we have exercises and assignments. Once again, the assignment, you're expected to provide an in-depth explanation of the rules, the discover rules, and the interpretation, the visualization part. But the exercise provides you enough information for you to be able to understand and use R for rule generation. And once again, I'm sorry for the sound, and hopefully for the next cycle, we will figure it out how to. I don't know what happened this time. I'm running from a VM. That could be it. Well, we will debug it. Elena, it looks like there's no other questions, and I guess we call it a night, right?
Oh, yes, I was in my phone mute. No, I don't see more questions. So if no more questions, we just end the today presentation. I'm not surprised because this is, let's say, the simplest, the most classical data mining algorithm from where all data mining, which is the most wide used. So I think people already find some, let's say, straightforward explanation, and there is no doubt. The thing starts when they start running the R script, and maybe we will have some question, and maybe we can take at the end of the week, somewhere Thursday, Friday, to do some help section with the running R code for association. Other than that, I don't have anything else.
Do you have any administrative stuff? Are we planning to have a TA session for this module? I believe we talked about that.
We will talk later, yeah.
Okay, thanks everybody. Sorry again for the voice quality. We'll do better next time around. And see you in class. And good night.
Good night.
Thank you.